Alright everyone, welcome back. Now it's time to talk about two-dimensional data. So far we've just been one-dimensional, and what's interesting about two-dimensional data is correlations. So we're interested how does one dimension of the data affect the other one. We could say the value of x, like if our two variables are x and y, the value of x has some information in it about the value of y. And there are definitely different types of correlations that like putting these pictures. Before we start, I'm just gonna ask you, so which diagrams do you think show a functional, like a strict functional correlation between x and y? Yes, exactly, this one here, top right. So functional correlation means like we can calculate one from the other. So we get a clear non-stochastical relationship here. Which diagram do you think shows positive stochastic correlation between x and y? Exactly, this one here at the bottom left. So if like x gets bigger, then y gets bigger as well. Yeah, bigger x, bigger y. Last question, which of these diagrams shows no correlation between x and y? You might have been tempted to say top right 2, but actually it's this one here. We'll talk about 2 in a second. The reason why 1 is true is because it doesn't matter if I tell you x is this value here or x is this value here. It doesn't matter, like in terms of y-axis, this looks really unimpressive. It's just always the same. So we don't, from x, we don't really learn anything about y. The one on the number 2 here is interesting because, you know, it's round. It looks like a disc or like a donut, and you might have been tempted and say, oh, it's like a round thing, so no correlation. But if you think about it, if I tell you x has this value here, a small value, then you know that y, the vertical one, is quite restricted and about around the center. If I tell you x has this value, you know that definitely there's no data in the middle. Yeah, so x gives us quite a lot of insight into y. Still, like we're gonna see, like the measures of correlation, the linear measures will give you a 0 here, but it's just a non-linear correlation. Okay, we can do the same thing that I've done here with the graphs and data points, just with a simple table. So think of students in a class and they sit a maths exam in blue and a physics exam in green, and then you compare the marks, and yeah, you would assume that people who are good at maths also do quite well in physics and vice versa. So how can we prove this? Like the raw data is not very intuitive, although we sometimes see, you know, the 2 4s, 2 2s, so it seems to be 2 5s to be somewhat correlated, but we can put it into a table. It's like the table corresponding thing to the graphs from earlier. We put the maths marks down here and physics down here. So basically, let's choose someone. Let's choose this guy here. He's got a 2 in maths. Okay, so this one here, and a 3 in physics. This one here. So that's this guy here. We put a 1 there, and then we do that for every data point, and then the table is like cross table fills. and with a bit of color highlighting we would see, there's a lot of the kind of the big numbers are sort of here in the middle, and out here to the side I get zeros, and here I get zeros. Yeah, so it seems like there's some correlation going on. That's all just like nice to look at. How can we like put it into numbers? And what we can calculate is the covariance. It quantifies linear relationships only, and the formula for it is very similar to the variance. If you look here, we have the mean value of x, and data point minus mean value of x times data point of y minus mean value of y. If you think this would be twice x, that you have the formula for the standard deviation, and normalizing by n minus 1. Now it's like mixed with x and y, and we can just try it out on this example here. So these are 3 data points for x, and these are 3 y's, and these are the mean values. I've shown you the calculation. It's a bit of juggling with numbers. So this 1 here minus the mean value 3 times this one here minus the mean value 4, and so on, and you get 5.5. And indeed, a positive number says large x predict large y, and small x predicts small y. So this is like a positive covariance. If we have 0 covariance, there's no linear relationship, and negative means like large x's predict small y's, and so on. In an example here, this data set has a covariance of 0.137, and maybe you wonder a little bit like why 0.137, and we're going to see in a minute the number itself is meaningless. It only matters smaller or bigger or equal to 0. Okay, have a go yourself. What's the covariance of this following data? Well done, -4 should be the outcome, and I've shown you the calculation here. It's a bit tedious to do it by hand. Use the covariance command in Excel, or use the MATLAB cov command. It makes it a lot easier. The problem with the covariance is what we just saw, is that the absolute number doesn't mean anything. So 0.137, what does it mean? So what we want to do, is we want to normalize the whole thing. So we can take the covariance and divide it by the standard deviations, both of them, in x and y. And what it means is the maximum value for the and this is called the correlation coefficient rho. So now it's normalized. Now we lie between -1 and +1, meaning if the correlation coefficient is equal to 1, we've got a linear functional relationship, maximum correlation, in the positive sense. -1 means we also got a linear functional relationship, meaning that like larger x's mean smaller y's, and for the rest in between we get like all shades of gray. 0 obviously means no linear correlationship. Look at these examples. So strict functional correlation, here we've got the line going up. Here we've got like quite a good correlation between x and y, quite a narrow elongated bar here, minus 0.9, and this is just random scatter of points, so here it's 0. Okay, give it a go. So I've given you not the raw number, but the two standard deviations, and the covariance is 4.5. Determine the correlation coefficient. Exactly, that one is easy. You basically just divide 4.5 by 2 and by 9, 0.25. Obviously we're going to do it with Excel, Coral is the function, or with MATLAB Core. Excellent. Next is linear regression. What is the idea of linear regression? Basically, we want to find a fit line. We want to find a red line that kind of interprets or represents our data points the best, assuming there's a linear relationship somewhere behind with a bit of noise or randomness in the whole system. So we want to find a function that's something like b times x plus t, and yeah, this is the y-axis, this is the x-axis. Yeah. So b is the steepness and t is my offset. That's what we want to find. First of all, I'm just giving you like 4 examples of fit lines, and you have to choose which one is the best fit. Exactly, number 3. Like, the human eye is quite good at doing this, so if you just take a ruler and do it by hand, you're most of the time quite close. You can clearly see, green is out of question, but yellow is a bit too flat. Yeah, this one needs to go up and this one needs to go down, and so on. So 3 looks just looks right. How do we calculate it? I don't want to like repeat, maybe you've seen it in previous courses. The maths of it is quite simple, finding extreme points, finding the maximum of a two-dimensional function sort of task. What we want to do, we want to minimize the distance from the line to the points, and if we mathematically calculate the whole thing, obviously like some derivative of the distance function needs to go to 0 for the maximum, we end up with this neat formula that uses all the things we've calculated so far. So our steepness b is our correlation coefficient times some standard deviations, and our offset is simply just determined by the mean values of x and y. So quite a simple 2 formulas to work with. Let's try it out, give it a go. Keep this here so you can see it. So determine the linear regression function of the following information. Okay, you probably paused the whole thing, and if you've done the calculation right, you're gonna get this steepness 0.6, offset 2. So in total our curve is 0.6x plus 2. Alright, but you've probably seen by hand it's a bit tedious. There are better tools like MATLAB. It gives you with the polyfit function or the polyval, it gives you a perfect fit straight away, especially when there's like large data sets involved. One interesting thing about the regression is, obviously, we always said y is a function of x, but why should it be the case that the vertical data points y depend on x? It could also be that the horizontal data points x depend on y. So we can do regression the other way as well, and this leads to kind of very similar formula as before, again with a correlation coefficient and the standard deviations and the mean values. Let's look at examples. So this is what it looks like if we use it for a large data set. You see the orange one is the version with like y depending on x. This is the orange one, and the yellow one that here is the x depending on y. And you see for this very correlated piece of data here on the top left, they're very close together. As the whole thing becomes less and less correlated, those two versions kind of drift apart. Here it's already a bit further apart, here even further, and here we've got like completely uncorrelated data, and obviously those two numbers just give us the mean values, so this y bar and this x bar, because there's no dependency. Yeah, we just predict the mean value. That's all we can do. Obviously, and yeah, you might have heard this in other courses as well, we can also do regression with higher order polynomials, not just linearly. Depending on your data and your problem, this might make sense, and it kind of works accordingly. The maths is like similar, but yeah, this is kind of going outside the scope of this course. Just if you're interested, our polyfit command in MATLAB does it all. You just need to give it the regression order number n here, and it does fits of all sorts of polynomials. Brilliant. That's it for now. Thank you very much for listening to the first lecture. I'm gonna try and put the next lecture up maybe next week or the week after, because Andreas is also putting stuff on quality management on, and I don't want to overload you too much. Okay, have a good time and have a look at the problem set I've put online for you. See ya.